Welcome to Matematika. Today I'm going to do polynomial functions and rates of chains. Let's do the first part, which is the polynomial function. So a non-constant polynomial function is a function that involves a variables raised to a non-negative integer powers. The standard form of a non-constant polynomial function is a function of x equals a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, plus a sub n minus 2 times x to the power of n minus 2, 2a sub 2 x to the second power plus a to the first x to the first plus a sub 0. Okay, where n is a positive integer in a sub n minus 1 and a sub n minus 2 up to a sub 2, a sub 1, and a sub 0 are real numbers, and a sub n is not equal to 0. N is the degree of the polynomial. Leading term is a sub n x to the power of n. The leading coefficient is a sub n, and a constant functions are also considered polynomial functions and also have a degree of 0. We'll get to know more on this term as we move on. We'll start with the definition here. Degree is the value of the highest exponent on a variable in the polynomial. Highest degree, highest exponent, okay? While the leading term is the term in a polynomial expression with the highest exponent of the variable. And the leading coefficient is the coefficient on the leading term in a polynomial. Okay. Reminder, we have to take note on this. The degree and leading coefficient together determine the end behavior of the polynomial function. That is how the function behaves as the input value approaches positive or negative infinity. And the degree, whether it is even or odd, dictates whether the function's ends have the same or opposite direction, while the leading coefficient determines whether the function increases or decreases as the input values approaches a positive or a negative infinity. This is negative infinity. All right. Let's get to know more everything in these examples right here. All right. Degree, leading term, leading coefficient. All right. Let's do number 1. Determine the degree, leading term, and leading coefficient. Okay, let's do this. Of the given polynomial, you have p of x equals 2x squared minus 8x plus 5. So, knowing to determine the degree is the highest exponent in the polynomial. So our exponent here, we could see that it's 2. That's the highest exponent because this is 8x to the first power. So our degree is 2. The leading term, okay? The leading term is the term in a polynomial where the highest exponent is. So the highest exponent is 2, then that term where the highest exponent is, that is the leading term. So we have 2x squared as the leading term. Leading coefficient. Okay. So what is the leading coefficient here? It says that the coefficient on the leading term is the leading coefficient. So our leading term is 2x squared. So the coefficient, which is 2, is our leading coefficient. So that answers for 2. Okay. Let's do number 2. P of x is negative 3x squared minus 4x cubed plus 7x to the p power minus 4. If you try to observe, the degree is not in order. 5 is right here. That's the highest. So we have to write it down in order. 7x to the 5th minus 4x to the 3rd minus 3x squared minus 4. Right? So this is our leading term. So the exponent there, that is the highest. The degree is 5. That's the degree. So the leading term is where the highest exponent is. So that is 7x to the 5th power. And the leading coefficient is the coefficient of the leading term, which is 7. There. All right? Let's do this. P of x is negative 7x to the 5th minus 3x to the 4th plus 8x cubed minus 2x squared plus 5. The exponents or the power are in order. 5, 4, 3, 2. All right? So that means the degree there is the highest exponent, this one. The leading term is where the highest exponent is. So that is negative 7 x to the 5th. And the leading coefficient, that is the coefficient of the leading term, which is negative 7. Fourth, p of x is 5x to the 4th minus 2x cubed plus 3x to the 6th plus 4. 6, the highest exponent. So we have to write this down in order. So 5x to the 4th minus 2x cubed plus 4. So this is our leading term. The degree is the highest exponent, that is 6. The leading term is 3x to the 6th power, and the leading coefficient is 3, where the leading term, the coefficient of the leading term. Now, as we need to know how to graph and what is the behavior of the graph, we need these 4 characteristics of a polynomial function. We need to know the degree, we need to know the leading coefficient, the end behavior, and the graph of the function. All right, in order to graph a function. Right? Okay. Let's start with when the degree is even. When the degree is even and it's positive, and the end behavior is as the function approaches positive infinity, as x approaches the negative infinity, and the function approaches positive infinity as x approaches a negative infinity, it rises to the left and to the right. Rise up, both of them rise up. Right? So, the degree and leading coefficient together determine the end behavior of the polynomial function. How the function behaves as the input value approaches positive or negative. All right? We remember that. And the degree, whether it's even or odd degree, dictates whether the function ends, that is the end behavior, have the same or opposite direction. And the leading coefficient determine whether the function increases or decreases as the input value approach the positive or negative infinity. And that is what we are going to understand in these four aspects of a polynomial function. Right? I will be doing the end behavior with you so that you might be, looking at it. Oh, what does it mean? Negative infinity, negative, and so on. So I will do this. I'll do the graph at the same time I'm pointing out which part of the table or the guide that we are looking for. So I'll start with graph number 1. All right. In graph number 1, when you're looking at the graph, first look at the end behavior of the graph. Okay. Both graph rise up here, rise up on the left side. When it's rise up, it's positive infinity. Okay. Now remember that in the x-axis, x approaches a positive infinity because it goes to the right. Okay? Right means positive infinity. Left goes to the negative infinity. So x approaches the negative infinity. So in this case here, as x approaches positive infinity, okay, the function of x approaches positive infinity. While here, as x approaches negative infinity, the function of x also approaches positive infinity. Okay, that is what we mean here. As the function of x approaches positive infinity, as x approaches a negative infinity. So here, x approaches negative infinity, the function is positive infinity. Over here, as f of x will be positive infinity as x approaches the positive infinity. So both, look at the graph function of the function. Both are rises up, rising. The left rise up, rises to the left and to the right. In other words, our degree here is positive. And the leading coefficient as well is positive. All right? Because it belongs here. It belongs there on the first one, even positive. So this is a smooth curve of a parabola. So it's a quadratic function. That means the degree is 2 to the second power. All right. Let's look at the graph number 2. Okay. First of all, I said look at the end behavior. Okay. It's facing down. The both end is facing down. That means the infinity here is negative. Right? Falls to the left and also right. Okay? Let's look at the degree and the leading coefficient. That means as x approaches positive infinity, your function is negative infinity. As x approaches positive infinity, the function is negative infinity. Right here. as x approaches negative infinity, the function of x is negative infinity. Right there. Negative, negative. Negative, positive, or positive, negative. And both falls, falls, fall, facing down. This one is both are facing up. Falls left and right. That means our degree is even right here, and the leading coefficient is negative. That's how you see that that way by looking at the table. Now, you want to know how much is our degree here. Just trace the curve. 1, it changed here. 2, and then it changed another one, 3, and then it changed that to 4. Okay? So our degree is 4. Every time the curve changes, you count that how many times. All right. Let's do this. First of all, look at the end behavior. So this is rising up. That means it's positive infinity. It is falling down, facing down. So this is negative infinity. So our function of x here is positive infinity. Our function of x is negative. A function of x here is negative infinity. As x approaches a positive infinity, you have a positive infinity in the function. As x approaches a negative infinity, the function is negative infinity. So where does it falls? Negative, negative, positive, positive. As x approaches a negative, the function is negative. As x approaches positive, the function is positive. One falls to the left and rises to the right. Rise to the right, right here, and falls to the left. So it belongs to the third category there. The degree is odd, right? And the leading coefficient is positive. How much is our degree here? We count the curve 1, it goes down 2, then here 3, then here 4, and then 5. So our degree is 5. It's odd, right? So let's do this in this case. Let's look at the end behavior. The right side facing down, so it's negative infinity. The left face up, so it's positive infinity. That means the function of x here is positive and the function of x is negative. As x approaches a positive infinity, the function is negative infinity. The function is positive infinity as x approaches a negative infinity. Going to the left, that's negative infinity. Going to the right, that's positive infinity. Okay, so this falls here. When a function is positive, as x approaches the negative infinity, right there. And if function of x is negative as x approaches the positive infinity. All right. So, in other words, what will be our degree? The degree would be odd. And then the leading coefficient is negative. Why? Because you look at the right side, okay? It falls to the right. Falls to the right and rise at left, right? So that means rise left, falls right. What would be our how do you go? How much is our degree here? Let's count how many turns. So 1, 2, 3. That means the degree is 3. Okay, that is how the curve goes. All right. Let's do this. Let's understand more. All right. Which of the graph match the following function? Right. If we look at the function of a, in a, I mean, f of x is negative x squared minus 4x minus 1. All right. Negative. The degree, okay, here. The degree is 2. Both of them has, the degree is even, right? Because it's 2. Okay. Right here in A, the leading coefficient is negative. So in B, the degree is 2 and the leading coefficient is positive. Okay. So remember in the table, when the degree is even and the leading coefficient is negative, how does our graph looks like? It falls to the left and to the right. Both are facing, for negative, both are facing down, and then both are facing up. Okay? So this is negative, so this is graph A. And this will be graph B, because the leading coefficient is positive and the degree is even. All right. That is the difference between a negative and a positive leading coefficient with the same number of degree. For number 3, it is cubic function. So one is positive, the other one is negative. So if we look at it's cubic, so it's odd. The degree is odd. Both of them have an odd degree. The other leading coefficient is negative. Okay? Odd degree and negative. That means the left side rises and the right side falls. So look at this. This is false. It falls down. So it's negative. And this is positive. That means this is graph A. Well, in graph B, the degree is odd, cubic, it's odd, and the leading coefficient is positive. All right. So what does a positive means? Here is a positive infinity for the right. And then it falls on left. So this is graph B. Okay. All right, let's do this. I will be sketching, just sketch. Okay. So, squared. Squared means a quadratic function. Okay, just a smooth like a parabola. But it's a negative. That means our parabola is facing down. Okay? The leading coefficient is negative and the exponent is even. Leading coefficient is negative and the degree is even. Even, negative. What does it mean? False in left and right. So this is negative infinity. Okay, in letter B, you have the degree even, second power, and the leading coefficient is positive. Positive, even. Okay, even, positive. What does it say? Rises both left and right. Maybe I could have my graph goes that way. So this is a positive infinity, positive infinity. For that, the graph faced up. All right. Function of y of x is negative x to the fourth, negative 12x cubed. So I just look at here. This is the one that I'm going to look at the first, the leading term. Okay. So the degree is even. Leading coefficient is negative. All right. Even and negative. Even and negative. It falls left and right. But the degree is 4. I have to make a 4 turns. All right. So I could start. So both of them are facing down. So I would say 1, 2, 3, 4. That is negative and negative infinity. Both are facing down. K of x is x to the fourth minus 3x squared minus 2x minus 1. So the degree is even. And the leading coefficient is positive. Even and positive, what does it say? Rise, both of them rise, the left side and the right. Rise up. Okay? So I would say it's 4. I do 4 turns. 1, 2, 3, 4. So this will be a positive infinity facing up. Right? G of x is x cubed. This is a cubic. Okay? So the degree is odd and the leading coefficient is positive. Odd and positive. Odd and positive. Falls to the left and rises up to the third power. So I have to make 3 turns. All right? Falls left, rises up. So this will be, I'm going to do this. Going to do that. This is a negative infinity and positive infinity. All right. Falls on the left, rise to the right. Okay. For the negative, how does it look like for a negative? I'm making a sketch here. So the degree is negative. Degree is odd, and the leading coefficient is negative. So what does an odd and negative means? The left rises and it falls to the right, and it's to the third power. So you have to make somewhat like a cubic one. 1, 2, 3. This is a positive infinity, and this is a negative infinity. That's how 1, 2, 3. Oh, no, I'm making a 4 turns here. That's wrong. Sorry. I have to make 3. 1, 2, 3. Okay. Oh, I don't like it. I'll have to change. All right, that way. This is a positive and this is a negative. Wait a minute. I have to look at this one right here. 1, 2, 3. Okay. All right. Okay, let's do this. Example 1. State whether the function of x equals x squared plus 2x cubed. 2x to the power of, I think this is to the power of 1/2 plus 3 is a polynomial function or not. All right, polynomial function or not. Now, to know whether a function is a polynomial, we have to check whether all variables are raised to the non-negative integer. So, raised to non-negative integer. That means the exponent should not be a negative, non-negative. Okay? So, if we try to look at, let's look at how it was raised. We have the exponent here. First, we have 2. Then we have 1/2. And we have 3. We have 0. Right? 3 to the power of 1. 0. Okay. So, in other words, 2, but 1/2. When x is raised to the power of 1/2, if you try to remember the rules of exponent, when your power is a fraction, that means your x is -2. And to make it into a positive, you have to get the reciprocal, and it will become, your exponent becomes a fraction. That means you have a negative, exponent here. So that means you could say 1/2 is not a positive integer, right? 1/2 is not positive integer. That means, what can we say about our function? X squared plus 2x squared, 2x to the power of 1/2 plus 3 is not a polynomial function. Okay, you must observe, because by looking at first, you could say, oh, it is a polynomial function, but you have to consider, the rules of exponents, especially whether it will come out into a positive or a negative exponent. Let's have number 2. Identify the degree, the leading coefficient, and the leading term. So we'll do first. Let's look at the function. P of x is -5x squared plus 4x plus 2x cubed minus 3. So the highest exponent is 3. That means we have to write them into order. 2x cubed minus 5x squared plus 4x minus 3. Actually, if we can look at it right away, but we have to be sure when we write this in order. Okay, so the degree would be the highest exponent, which is 3, and then the leading term is 2x cubed, and the leading coefficient is equals to 2, where the leading term is, the coefficient of the leading term. And that's how we answer that question. All right. Let's do question number 3. Given the polynomial function below, we have you're given a graph. Find the average rate of change over the following intervals. You are given an interval of -3 to -2, then -2 to 0, then 0 to 2, 2 to 3. Okay, rate of change. Remember, in our previous video, when we did the rate of change, by doing the average rate of change, all right, we use the formula of function of b minus function of a over b minus a, okay, where a is one of the endpoints here because we are given a graph, and a is the endpoint of the other interval. A is one endpoint of the function, of the interval. Okay, we could say the interval of the interval, and b is the other endpoint of the interval. Okay, so let's do this. We'll start with the interval of the first interval given between -3 and -2. All right, so I'm going to start with the other end would be, I will make this as the A and the B, okay? A and B. All right, since B is greater than A. All right, so I will do this. Function of -2 for function of B minus function of A, which is -3 over -2 minus a -3. Okay, let's look at where -2 is. -2 is right here, right? Let's go down and look at the function, the output. When it's 2, -2, that means the output is -20, right? Then let's look at when it's -3, right here. If we go here, so this will be 70. Okay? When it's -3, it's 70 by looking at the graph over -2 plus 3. So you have a -90 over 1. So our rate of change in this interval is negative 90. Okay? Let's do the second interval. When it's between negative 2 and 0. Okay? That means this will be the B and this will be the A. So that means f of B would be f of 0 minus f of negative 2 over 0 minus negative 2. What's the function when it's 0? When x is 0, the y is also, the function of 0 is also 0. When it's negative 2, it's negative 20, right? So 0 minus a negative 2, that is a positive 2. Okay, so we have 20 divided by 2. So our rate of change is 10. Oh, yeah, 0 plus 2, it's 2. Okay, I will do the third one. It's 0, between 0 and 2. So this is B, this is A. So function of 2 minus function of 0 would be equals to 2 minus 0. So function of 2 is, function of 2 is 20, right here, right here, it's 20. So 20 minus 0, then 2 minus 0. So 20 over 2, that is 10. And the last interval, we have 2 to 3. So BA, function of 3 minus function of 2 over 3 minus 2, right? So you have, what do you have here? When it's function of 3, it's right here. So we can extend. Maybe this is also negative 70. So that would be a negative 70 minus 20. Function of 2 is 20, right? It's negative 20. Oh. Yeah, it's 20. 3 minus 2, it's 1. So a negative 90 over 1, it is 90. Negative 90. Right? So what have you observed? The average rate of change in the interval of negative 3, between negative 3 and negative 2, and 2, negative 3 are the same, right? Same, right? Like this, negative 90. Same as the intervals of negative 2 to 10 to 0 and 0 to 2. They are also the same interval. So in other words, The intervals around the point of inflection are much slower than the others. Here, right here. Where is our point of inflection? The point where at this point and at this point right here, where the curve, this is facing up and somewhere here is facing down. It's facing up and then it's facing down. So in the point of inflection are much slower than the others. In the point, the intervals around, you could say the intervals around the point of inflection are much slow than the other intervals, than the others, meaning than the other intervals. Okay, that's it, what you can see. So you make your observation. You're just asked to find the average rate of change over the following intervals. So you made your observation that the intervals between -3 to -2, 2 to 3 are the same. Might as well the interval between -2 to 0 and 0 to 2 are also the same. Okay? Determine the end behavior of the function. We want to end behavior of the function. Let's go back to the function here. We want to determine what happens to y values as x, and the x values are very small and very large. Okay? Very small and very large. Look at this. And behavior here, x gets very large because as x approaches positive infinity, it, you know, it has an end behavior of a negative infinity. And here it's positive in infinity as x gets smaller, meaning as x approaches a negative infinity. As x approaches a positive infinity, the end behavior of x gets very large. Okay? As x gets very small and y gets very large. Okay, I'm gonna write it here. As x gets very small, that is somewhere here. Okay, what happened to the y value? It approached to a positive infinity. The x is negative, while the y value approaches the positive infinity. That's why it becomes very large. So as x approaches a negative infinity, y is positive infinity. While as x, the other side, as x gets very large, see that our x here approaches, I'm gonna make this, as our x approaches positive infinity, very large, y, what happened to our y here? Okay, y gets very small. Why very small? Because you see that the function is negative. As it goes down and down and down, the value of y becomes smaller. Okay, so you could say as x approaches a positive infinity, y, or the function, approaches a negative infinity. Okay? You have that. State the domain and range of the function. So what can you say the x values of the function? As the range represents the y values of the function. Okay? Of course, the domain. The domain is the x, represents the x values of the function. And range, that is the y values. Okay? Represents the y values of the function. Recall that the graph of a polynomial function is one smooth curve and continuous domain. Okay, as the polynomial is defined, the number of input and the domain, like our domain would be negative infinity and positive infinity. Okay, sum of the graph when the function is smooth continuous curve, and the continuous to be defined as the left, as the x values get smaller and smaller, on the right as the x value gets large. As the x value large, the function become the range becomes smaller and smaller. Since the y values continues to increasing small and increasing large, so our range would be still in this condition from negative to a positive infinity. So I could say the domain when the infinity is negative and it increased to a positive. That is what we mean by that, by here, in this condition in the graph, right? As x increases, okay, as the domain increases positive infinity, the range is negative infinity. As the domain decreases, that is negative infinity, the range increases. That's a positive infinity. Okay? Positive and negative infinity for range, and for the domain, still a negative and positive infinity. All right. I think these are the information needed in the knowing about the polynomial functions. We'll get to know more on polynomial functions as we move on to the second part of polynomial functions and the rate of change. Okay, then I could say that if I can do it, so can you. Please hit the like button and also the subscribe button. See you in my next video.